All right, how's it going?
Good. How are you, Nick?
I'm well.
Are you?
Yes, I am.
Okay.
How did the meeting go?
Oh, it was good. Man, Izad is good.
Izad is good?
Yeah. Man, it's like the most productive meeting I've ever seen.
Really?
Yeah, he's pretty amazing.
That's awesome.
Yeah, I mean, he's been in industry a long time, and I
Knows
think
the right stuff to say.
he knows how to organize people and make things run smoothly and stuff like that. And I'm really glad that he decided to go into teaching, because otherwise I would be totally lost. But yeah, that was a cool meeting.
I kind of wish like I was there.
Yeah, I met a bunch of cool people, and hopefully we got some good stuff done. So that's all good. All right, so so I'm still in the process of grading your programming assignment. I'm about 2/3 of the way through, and I apologize for that. It was an interesting weekend, so I will get those done today or tomorrow at the latest. But they are looking really good so far. Everybody's done a really nice job on them. The deductions are mostly just kind of nickel and dime things, like most of the problems I'm seeing are around the cheat detection. So
Wait, there's a cheat detection?
yeah.
Oh, not the weird GA.
No. So the person guesses a number and then they change their guess
Got it.
while it's running.
Would that have worried you?
Hypothetically. Yeah. Yeah. So I'm not seeing any major issues with the high-low game so far. So that's awesome. Any questions up to here?
How's your day?
My day's great.
I might
Thank you.
need help. I might want to redo one of the PAs, PA2.
Yeah.
Yeah, because I'm kind of loose on that.
Okay.
Yeah.
PA2 was C.
Yeah.
Okay.
I think I just struggle with C, honestly.
Yeah. Can you come by office hours sometime?
Yeah.
Okay, come by. We can go through it. We can talk about it.
Okay.
For PA4, like the input, can the input string like be as long as we want when we
Mhm.
type in? Okay, so we learn how to do that.
Yeah. There's an easy way to deal with it, and I don't know if I spell it out explicitly in the assignment, but let's take a look at the assignment. And somebody asked a really important question, and I was in this section. I need to mention it in the earlier one again. So you absolutely do not want to read the entire file into memory and then start trying to process it, right? That's definitely not going to work with War and Peace and things like that. But really, you can do everything that's mentioned in the assignment by ingesting one character at a time. Okay? Just start pulling in one character at a time. Use getChar. All right, bundle that in your super duper getChar. But you're really just reading one character at a time, and if you're building up a phrase and you've already read 200 characters into it, you can keep reading, but just don't save those extra characters. Now your input could be, another 100,000 characters. You're just throwing those characters away. So you don't really need any arrays bigger than, say, 201, 202 characters. And if the whole thing is on one line, if it's War and Peace as a single line file, or if it's broken up into 10,000 lines, it really makes no difference to you, because your new lines are being converted into spaces by your super duper getChar anyway. So it's going to look like just one big long single line of input. But if you try to use fgets, right, then you're making things hard on yourself. Because fgets, you got to tell it how many characters to read, and it might chop off halfway through a word, and you're going to have to notice that and put the pieces together and so on. So definitely go single character at a time. And then the line length shouldn't be an issue. All right, other questions? All right, so let's talk about your ODP. So 418, you're writing a function named move. It takes in a character string, it gives you back a character string. So declare both arguments as char star. Assume the first argument exists, it's got stuff in it. Assume the second argument is just junk to begin with. And your goal is to basically take the letters, the characters in that first argument and just shift them left one spot. And that first character gets wrapped around and takes up the last spot in the array. So HELLO becomes ELLOH. ABCDE would become BCDEA. Right, so move everything down, take the first character, copy it to the end. And there's a fairly straightforward way to do this, and there's a number of really confusing, complex, difficult ways to do this. Which one should we talk about? Let's talk about the most confusing way. No. Let's talk about the more straightforward way to do this. So this is move. And let's suppose your input argument is called in and your output argument is called out, which is not the most confusing way to name them. So let's look at what in might look like. Let's say your input is A, B, C, D, E, a null terminator, and then who knows what stuff. And let's suppose originally you're given this output variable, so you know it points to something that you're allowed to write to, but you don't know what's initially stored in that location. So let's just suppose that this initially contains unknown junk. And when you're testing it, I suggest before you call your move function, copy 20 question marks into your output array. Copy ABCDE, null terminator in your input array, call move, and make sure that your output array looks good afterwards. Okay, so what should happen here? The letter B should get copied here, C should get copied here, D goes there, E goes there. The letter A should come over here. And finally, a null terminator should get written here. And it feels like there should be, a one-line C function that does this. Just write a for loop and do something, right? There really isn't. It's really sort of three things that you want to do. And if you think of it in terms of doing these three things, you can code this up pretty quickly, I'm sure. Okay, the first thing is, starting with the second letter, copy it to the position before it in out. So for I equals 1, I less than string length, right? Output bracket I minus 1 equals input bracket I. Just copy those things over. That's the first thing. The second thing is take the first letter of your input, copy it to the last position of your output. Where do you put it? You got to play around with it, right? But string length of input minus 1 is probably a safe bet. And then the third thing is you've got to put a null terminator in your output. Where do you put that? Play around with it, but probably string length of in is a safe bet. Okay, but really work this out on paper. Okay, before you write the code, think about what these three steps are going to be. Sketch out some C code. The for loop is one for loop. Moving the first thing to the end and writing the null terminator, those are one statement each. It's not a lot of code, but you got to get it just right. Is it string length minus 1? Is it string length? Is it string length of in or string length of out? Do I loop from 1 or 0 or less than 1 and so on and so forth, right? Lots of details. I want this to be completely non-magical to you when you're done with it. I want you to completely understand the code that you've written. It may be a for loop and 2 assignment statements, okay? But I want you to feel really confident before you assess it that you're going to get 100%. Okay, this is a good exercise. This is good practice in terms of, say, writing code on exams. So sketch this out on paper. Think about these three pieces of the algorithm, copying those over, moving the last letter, and then putting the null terminator. Write some code, and then run it on some test cases. Make an input, set your output to a bunch of question marks, and step through it on paper and make sure that this turns out to be B, C, D, E, A, null terminator. And then think about edge cases. And there's sort of a main case and two edge cases. This is the main case where you have a bunch of letters, you do these 3 steps. There's an edge case, which is where your input is a single character. Because if it's a single character, we don't want to copy character 0 to character position -1. That's a seg fault, right? We really don't have any shifting to do. All we've got to do is take the last character and copy it into the first character and copy it into the last position. But since the first character is already in the last position, our output should end up looking exactly like the input. All right, so if you rotate something that only has one spot, it doesn't change. So this is an edge case, and your general algorithm may throw a seg fault if you don't look for this case in particular. Your second edge case is when your string is completely empty. And in that case, again, you simply want the output to be a copy of the input, just something with a null terminator in position 0. So you probably want to check explicitly for this, explicitly for that, and then code up your 3-step general process for the third most general case. So I would say work that out, run it on paper, make sure that it works, and then write a test program. Write a main program that sets your output to a bunch of question marks, sets your input to A, B, C, D, E, calls the move, prints out the new value of output, throw some angle brackets so you can see if there's spaces, you can see exactly where it ends, and make sure it's B, C, D, E, A, and run that with a couple of different strings, including a string with 1 character or a string with no characters. There's no fgets anywhere in here, there's no scanf anywhere in here. You're just manipulating an array in memory. Okay, it's all about just doing index math, which is kind of inherently really confusing. It's one of the more kind of error-prone aspects of writing code, but it's a really useful thing to get good at. The other thing I'll warn you on, don't try to use string length on out, right? If out is a bunch of question marks, string length is effectively random. You can use string length on in though, right? That would return 5 if that's my input, and that should be what I ultimately end up with the string length of out being. Did you have a question?
Oh, yeah, so would you recommend using arrays for those characters?
They are arrays, they're character stars.
Oh, that's right.
So yeah, they're exactly arrays.
Keep forgetting.
Yeah, that's weird about C. All right, does this make sense? All right, so try it on paper, work out the algorithm, run some test cases, write some test code, then go ahead and assess it. All right. Let's see. All right. There was a question in the previous class about.
It says cannot run program MLE, which means maybe there's a typo in the SS. Because I tested it with your thing and
Interesting. anybody run the ODP yet?
Yeah.
Did it work?
Yeah.
Interesting.
What way did you do it?
No, it just says cannot run program MOV.
Should be MOVE. That's what it's set up to run. And that's definitely there.
Have you tried turning it off and back on again?
There you go. 3 times, right? What's your main program called?
Oh, it's MOV, which
It should be okay as long as you called it that.
what I did. Oh, now it works. It let me assess MOV. I don't think I have a file that's called MOV.
MOV might be a built-in or not. Yeah, assess, no bets, no guarantees if there's any typos. All right, so a question came up in the previous section about dealing with these 2-dimensional arrays. Has that been a problem for anybody?
What was the question?
How to deal with 2-dimensional arrays like the dictionary? So if you have your dictionary in main, it's just character, dictionary, 1000, 201. The trick to being able to pass this to functions and work with it is just use this declaration everywhere that you define the argument type. Don't use char star star, don't use char star bracket 201 or something. Just use character, dictionary, bracket 1000, bracket 201, or whatever you decide to call the argument.
So why does the car star star work in like arg?
Because that really is a char star star. It does not, argv does not have fixed dimensions,
Okay.
right? Because it doesn't know how many arguments you have and it doesn't know how long each argument is.
So does it decide how much memory to space out when it receives that information?
Yeah.
Okay.
And that's really an array of pointers. Argv is really like, it's an array, and this points to your first string, this points to your second, and so on and so forth.
Yeah.
A 2-dimensional array is really just a bunch of things packed into memory one after another. For a 1-dimensional array, they're identical. For a 2-dimensional array, it gets different, and the compiler will complain if you try to pass this to a function and the function says, I'm expecting a char star star. It'll yell at you.
So if we have a phrase that's just like and, or like a one-word phrase, does it take up that entire 200?
Yeah.
Okay.
Enjoy it. Memory is cheap.
Nowadays.
Yeah. Yeah, don't do this in the 60s. Yeah, and that's why we would normally use a char star star, but it makes the code a lot more complicated. And when you prototype your function, if you got like a print function, so print dictionary, you can say char bracket 1000 bracket 201. All right, that's a valid function prototype. All right. So let's talk about modularization. And our goal here is to get to talking about what's called a makefile. So let me give you some setup first. And this is not what you're going to bump into in PA4. You'll bump into this on PA4 on a much smaller scale. But imagine that you are working on a very large project. And let's say it has 2,500 C files. So So there's main.c, there's print.c, there's does some weird thing.c, there's I get paid by the line of code.c. You got 2,500 files containing C code, right? And each of these is probably a separate function or a set of functions. And maybe there's a main.c that calls some of these functions, and some of these functions call other functions. So you got all these files together. And if you compile everything, you get this thing called Rogue. It's a really fun game to play, right? So you take this source code and you put it out on the web, and you say, hey, this is open source, anybody can use it who wants it. And so somebody comes along and they download this thing from GitLab, from your repository, and now they've got 2,500 .c files sitting in their directory. And they want to compile it to make Rogue. How do they do that? And you can't just give them an executable because you're giving them source code. If they're downloading on a Raspberry Pi, your executable on an x86 machine will not run. Okay, they need to go back to the source code and they need to compile it on their Raspberry Pi because that will produce code that runs on the Raspberry Pi. If they're from the past and they download this to an IBM 360, they have to recompile it on the IBM 360. So how do they compile 2,500 .c files? Well, you know, you can hope that the world is nice, and you can say gcc-o rogue star.c. There's two problems. One, that may not work. Some of those C files may not actually be part of your executable. They may be test files. I get this in some people's submissions. They have different versions of their code. They might have 5 main programs. Only one of them actually is supposed to work. So you may need to be more tactical than this. The other problem is 2,500 .c files, that takes a long time to compile. Now you got to do it the first time, but let's say you do this and you get your version of Rogue and that's working great, and now you want to change something. You want to change one line in one file, like maybe in the main program you wanted to say welcome to Nick's dungeon instead of just welcome to the dungeon. So you change main.c. What do you have to recompile now? Maybe everything, maybe just main.c. So every time you make a change, if you have to recompile all your .c files, that takes a long time. And now extend this to a team of people working on, say, the Linux kernel with, you know, tens of thousands plus of C files and various dependencies and constantly needing to rebuild the kernel, right, the executable piece of this whole endeavor. This is going to be really time consuming. Right, so when Red Hat Linux was a thing and you had to recompile your kernel, it would take like 5 or 6 hours because machines were like 75 megahertz. So we want to be able to develop programs that have lots of different pieces, but when it's time to build the executable, we want to do that in a way that does as little work as possible, but does enough work to actually give you the executable. And as the person who's writing this code, you know what that might mean. As somebody who downloads this, they have no idea. They just see an old directory filled with all these files. What do I do with this? Well, maybe somebody else has done this. I'll do something else today. So a makefile is a description of what has to be recompiled when, under what circumstances, in order to create a new executable. And as the person developing a project, you create this makefile, and it lets other people compile the code, make changes, recompile, and so on. And to do it in a very efficient way.
So what you're talking about, is that basically like when you install a program through an executable file on your computer? Like when you download an executable but then installs?
When you download an executable, it might be doing something like this in the background. Yeah, it could. This is really for when you're starting from source files. And so typically if you download something like, say, in a Windows environment or more of a closed system, you don't get source files because people want to sort of hold on to that so they can sell it to you, right? But there's still a process to go through to take the stuff that is downloaded and turn it into something that runs on your system. And you could actually use something like a makefile for that. The way we're going to use a makefile is really starting a step earlier, which is the source code. But yeah, it's a similar process. And let me give you the picture of what really happens when we compile a program. So you've got a source file, which is a .c. And here's my main .c. This is for the stick picking game. So my main program is really small. It prints out a welcome, it processes the arguments, decides how many sticks to play with. If there is a problem, it gives up. Otherwise, it shows the pile of sticks, and then it plays the game. Really, really small main program, right? Fits on half a screen, easy to look at. I can throw in lots of comments and stuff like that. But it's a nice small bite-sized piece, 14 lines, including white space and brackets and things like that. And I have a bunch of .c files in here. I've got 5 pieces broken up into. So I can compile them all like this, and I can do my stick picking game. Okay, so what happens when we do this compilation? Well, we start off with this source file, and we compile it. But actually something happens before we compile it. We've got things like this number sign include, right? And we've said this basically takes the contents of some file called stdio.h and it pops it into my file right here. Okay, stdio.h is a big long file sitting under /user/include, and basically the contents of that file replaces this one line in my program. And I have a file stick.h, we'll talk more about that in a minute. The contents of that replaces that second include. So there's a thing called a Preprocessor, CPP. And CPP's job is to go through your source file and do things like number sign include. If it finds a line that says number sign include file, it'll find file, open it up, read the contents, and replace that number sign include file with the contents of that file. If you know how to use defines, we can use number sign define to create a symbol. It'll replace those symbols with the value of that define. So this is called pre-processing. This happens before the actual compilation starts. And it basically turns your source file into a bigger source file. And this is the CPP preprocessor. I haven't tried this in a while. So here's main.c, right? Let's run it through the preprocessor. And let's make something called bigger main.c. Okay, if we look at bigger main.c, it's 813 lines. And it's got, you know, these type defs of unsigned character and double underscore quad underscore t and fs word underscore t and all stuff. This is my C program, right? I didn't write this stuff. It got included from standard.io.h. Right? It's got definitions of printf. Right? There's the function prototype for printf. I didn't write that. It was inside stdio.h. So my little .c program, which was like 14 lines, got turned into an 813 line C file, which ends with, you know, my humble lines of code, but has all this other stuff in it. So the C preprocessor turns your source file into a typically bigger source file, and then that gets compiled into an assembly file, which we can think of as a .asm or a .s, and that gets assembled by an assembler into an object file, which is a .o, and then your object gets linked with things like the actual code for printf. So that goes through a linker and creates an executable file. And all of this happens when we just say gcc-o executable source files. But all these different steps are taking place. Okay, why do we care about this? Because this part up here is slow. This part down here is fast. Preprocessor, right, we had a 14-line file that turned into an 800+ line file, and then all of those lines had to be compiled. Those lines contain comments, they contain white space, they contain variables that need to be resolved. There's all kinds of things that happen in here. That's a lot of stuff to chow through, right? Bigger main.c is 18,000 bytes, 18,000 characters. The compilation is complex because it's reading human readable code, turning it into assembly. The assembly is human readable. It's not as high level, but let me show you what the assembly looks like. Right, there's what the assembly language looks like. And it's still human readable if you're the kind of human who reads x86 assembly language. It's got spaces, it's got its version of comments and stuff like that. That has to get translated into ones and zeros. So all of this stuff is sort of converting it into a pre-digested form that the linker can chew on. Once we get to the .o file, that's really easy for the tools to work with because that's binary. So the linking phase is usually really fast. So we kind of want to avoid doing this part of the process any more than necessary. So here's the deal. You got your 2,500 files. All of them are .c files. You change one .c file. You need to recompile that. That takes doing this stuff. But once you compile that to a new object, now you've got 2,500 up-to-date objects. You want to link those together. That's really quick. Okay, that's going to be a much faster development. Then I changed my one .c file. I'm going to recompile all 2,500 and go out to lunch because it's going to take a half hour. So the goal of makefiles is basically to say, if we have to do all of this stuff, if we have to go from the .c file to a .o, we will do it. But if we don't have to, let's not do it. Let's only compile the things that need to be recompiled. But because the dependencies between things can be very strange, the user doesn't know what has to be recompiled when. So we create this thing called a makefile, which will tell the user exactly what needs to be compiled under what circumstances. So here's what a makefile looks like. It's a set of pairs of lines. The first line starts with something we call a target. That's the name of the thing we're trying to build, followed by a list of dependencies. Things that need to be up to date in order to build that target. All right, target and dependencies. The second line has to start with a tab and is followed immediately by the command that we use to build the target, assuming those dependencies are satisfied. And this pattern just repeats. We have another target with a list of dependencies and then a tab followed by a command and so on. All right, so let me show you what we have in here. Let me get rid of bigger main. Let me get rid of stick. All right, I've got 5 .c files. So main.c was the main program, and I think we looked at this when we were finished up with PA2. Processes the arguments, decides how many sticks. If there's a problem, num sticks will come back as 0, so it'll exit. Otherwise, show the pile of sticks, play the game. Our start function, big monster, 53 lines, takes an argc, argv, and does all the stuff that it does. Okay, this is slightly different from the actual PA2 assignment because this is a few years old. But it checks the argument count. If there's more than 2 characters, gives you an error message and it returns 0. That's the flag saying, get out of here, something went wrong. If there's exactly 2 arguments, it parses the argument, turns it into an integer. If it's not an integer, it says not a valid integer, and it returns our flag 0. Here I wanted the number of sticks to be at least 1, so if it's less than 1, prints an error message, returns 0. I also specified a maximum number of sticks, so if the number of sticks is bigger than the maximum, it gives you an error message, returns 0. Otherwise, it returns the number of sticks to play with. And that's all if argc is equal to 2. If you didn't put a command line argument, argc must be 1, so ask how many sticks, do your fgets, do your scanf, repeat the check to make sure it's positive, not bigger than the maximum, and then return the number of sticks. But all of that is buried inside this one line of code in my main program. Right? So looking at this, I could look at 53 lines of code before I even get to where the game starts playing. Right? That's hard to work with, it's hard to edit, it's hard to debug, it's hard to look at. Right? And logically in my main program, what do I want to do? Well, I should have a comment here, right? Decide how many sticks to play with. And the details don't matter to me. It's a system diagram. What goes in is argc, argv. What comes out is the number of sticks or an error code. All right, same with show sticks. So before we start playing the game, I want to show the number of sticks. So I call show sticks, and it does the for loop, prints out the pipes, prints out the number of sticks in curly brackets. And then I play the game. And playgame.c, which is apparently hard to spell, 27 lines. And so it, loops while there's sticks left, gets a user move, adjusts the pile, sees if someone won, shows the sticks, gets the computer move, adjusts the pile, sees if someone won, shows the sticks. And it loops on that forever. Right, and it uses show sticks twice. I use show sticks once in main, so that was a nice function. All right, so so we've got all this stuff. Our start function has this max sticks. All right, so I set it up so you could specify a maximum number of sticks. And where does that come from? Well, that's set up inside stick.h. The other thing is main.c, didn't look like I prototyped any of these functions, start and show sticks and play game. There's no prototypes up here. Those are also in stick.h. So now let's take a look at stick.h. So what's in there? Function prototypes and a define of max sticks. Okay, so you know what function prototypes are, right? If you prototype a function that you don't end up using, that does not do any harm. It gives the compiler information it doesn't use. So I can prototype all my functions in here, and unless, I had some other version of show sticks that I was going to use, which I shouldn't, right? Listing all my function prototypes in one file, not a problem. This define is something that basically says anytime you see this symbol, max sticks uppercase, replace it with a 40. It's not a variable. It doesn't take any memory. It's part of the pre-processing. So before my code actually gets compiled, this function down here with max sticks, this will get replaced with a 40. You understand the difference between that and a variable?
You can't modify that then, right?
Can't modify it at runtime. The compiler will actually see the statement if numsticks greater than 40. Print too many sticks, maximum equals %d, unquote, comma, 40. Right? It's just a symbol, it just gets replaced with some other symbol. That's pre-processing. right? So that's what the code looks like when it actually gets to the compiler. If numsticks is bigger than 40, print too many sticks. All right, so what do we put in .h files? Function prototypes, defines, that's pretty much it. Don't put executable code in there. If you put executable code in there, you may as well just put it in the file that you're including this in. And chances are, if you put executable code in here, well, one of two things will happen. One, you'll get compile errors. Or two, you won't get compile errors, which means you're misusing the include file. So either way, it's not a good outcome. So function prototypes are fine, defines are fine. But don't put in, you know, an actual function, print stick, curly bracket, etc., etc. All right, so I've got 5 .c files. I'm trying to make an executable called stick. I know that I can do this, but that's expensive. If I change my main program and I want to rebuild my executable, this recompiles all 5 of my programs, even though I only changed one. In reality, if I change main.c, I should only have to recompile main.c. So here's a more nuanced way to do this. So let's get rid of stick. So GCC-C says compile down to an object, but don't go any further. So on our picture, this piece up here is GCC-C. It starts with a source file, it brings you down to an object. GCC-O says also go ahead and link the objects together, give me an executable. So we're going to say GCC-C, that's going to do this long, slow part of the compilation. And when I say GCC-C star.c, I get these .o files, main.o, getUserMove.o, stick.start.o, right? Those are the objects. And now I can say GCC-O stick star.o, and I can run my stick game. Now let's say I want to get rid of that welcome message in the beginning. It says, welcome to the stick game. I don't like that. I'm going to edit main.c. I'm going to get rid of that print. Okay, what do I have to do to build my executable? All I have to do is recompile main.c to an object. GCC-C stick.c, or main.c. Now I've got a new .o file, now I just have to link those together. And now when I run my stick game, I've got the new version. I did not recompile start.c, showsticks.c, playgame.c, just main.c.
So this isn't completely related, but the object files, is that in correlation with like object-oriented programming?
No.
There's not a connection there?
Not that I know of, although if I thought about it deeply enough, probably I'd figure one out.
Okay.
But I can do that with anything.
Yeah.
But I don't think so. There's probably some historical reason why objects in like Java are called objects, though. It
Okay.
might be related to that.
So you compile your changes but link them together. They're already compiled.
Yeah, yeah.
Make them hold hands.
Yeah, exactly. So the trick is, right, how do we know which things have to be compiled when we change what? And if I change stick.h, which has function prototypes, I probably have to compile a bunch of .c files, even though I didn't change any .c files. Any file that includes stick.h probably needs to be recompiled. So this makefile business is a way to systematically describe these dependencies. So if I want to make stick, what has to be recompiled? And so let me show you a makefile that would work for this. And let me get rid of this last stuff. And this is more complex than I meant it to be. But here's the basic setup. Our first target is called stick. So I want to build something called stick. And in order to build stick, I need up-to-date versions of these 5.o files. And if I have those things, Here's the command to give me my stick. gcc-o stick, and then just all of those .o files. But in order to do that, I need to have start.o. And it needs to be up to date. Okay, what does start.o depend on? It depends on start.c and it depends on stick.h. And if I have both of those, I can say gcc-c start.c, and that'll give me start.o. And so ignore this other fancier stuff for now. Same thing with main.o. Main.o depends on main.c and stick.h. And if I have those, I can say gcc-c main.c. So there's our first sample make file. And we'll start with this tomorrow. We'll talk about what exactly this is saying. And we'll talk about how this gets used, and then we'll start editing some files and see how this does just the right thing in each case. And then we'll go ahead and we'll embellish it with those things I just deleted and make it more general purpose. And that'll be sort of our first overview of make files. So you're going to need to do this for PA4. You're required to have a make file to go along with your code. And make files can be really simple, okay, but there's a right way to do it, and then there's just kind of a lazy way to do it. And it's good to understand the right way, because you'll definitely see make files on the exam also. So we'll dig into this a lot more tomorrow. All right, so I'll see you next time.
Hey, look, Nick.